Hello everybody. So this is the first lecture video out of 4 that we're going to do for vocal physiology. I'm sorry I can't be with you because of all the coronavirus stuff, but we're going to online classes. So just so you know, remember we're doing this asynchronously, so we're not going to be meeting at our normal class times, but I want to make sure that you know that I'm absolutely 100% available if you need to ask me questions or you want clarification about any of this stuff. A lot of what usually happens with this class is that there's a lot of questions that arise in class that are really easy to clarify if we're like in person, but we don't get to do that in this case. And I'm not going to do any kind of like discussion board or blog posts for you all. But what I am going to have is questions that you have to answer with each of these videos. And because I'm not going to give you a test for them, they're going to be a little bit more involved than is there's going to be more questions for them. And it's really good if make sure that you do them on your own because academic honesty is really important with this. I know it's easy to maybe kind of just like share answers with everybody, but I can usually tell when you all get the same answers because you word them very similarly. So I don't want to mean that as a threat. What I mean it by is that it's worth it taking the time to really find the answers for them because it'll help your own musical journey and you'll really start to understand why this stuff is important. If you just kind of gloss over it and just follow along with the videos, it's not going to be beneficial to you and you'll just be doing the class for a grade. And you know, it's worth it I think to have this knowledge because we know so much more about it than we did before. So, with that, I would like to go into talking about resonance. So I'm going to be revisiting things that we talked about in class already. I'm starting this whole chapter just because that was so long ago and this builds up on information that we've been involved with. So I just want to do it as a refresher. Before I do that, I'd like to read the questions that are going to accompany this. So there are 6 of them. The first one is, what 3 aspects determine the efficiency of a resonator? Next is, why is phase shifting important for a quarter wave resonator? Describe source filter theory in your own words. How is a formant different than a resonance? How are resonant frequencies raised or lowered according to the perturbation theory? And how does how does perturbation at different points in the vocal tract change vocal style and timbre? And that has to do with the Tylee Ross video that we're going to watch at the end of the video, of this video. So just make sure you watch all the way through. All right, so let's get started with the PowerPoint. So resonance. What is resonance? Resonance is the enhancement of an acoustic wave due to reflections from another surface. So the sound comes out of the speaker, right? Goes towards the wall and then bounces back. That's what the resonance is. So we have the first sound wave in blue and the reflected sound wave in pink, red, whatever that color is. And then what happens is those sound waves, the one from the speaker and the one bounced off the wall, will interact with each other. And so we can look at that with some math. I know that's y'all's favorite. But when they're bouncing off the walls, they will end up let's look at this one. They'll end up creating sort of an aggregate of them, right? So if we move, well, that's changing the amplitude. But if I move the wavelength, sorry, we want to be looking at this one. My bad. So if we're changing what phase this green wave is in, so when I move this slider over on the left, what happens is it changes where that green wave is at in this phase, right? So we're moving it towards compression right here. And so when it matches the red wave, we get the composite of those stacked on top of each other in this dotted line, right? And then when they don't match each other, they cancel each other out, right? So you can have constructive and destructive resonance with this, right? So constructive is when they're combining together, and destructive is when they're canceling each other out. So standing waves are kind of like the normal way that we will see resonance. It's the simplest way to look at them. And so the definition of a standing wave is a single frequency mode of vibration of a body or physical system in which the amplitude varies from place to place, is constantly zero at fixed points, and has maxima at other points. And so what's happening is that the sound wave is bouncing off of walls on two sides of a chamber. And if it's equal to the length of that sound wave or its divisions, right, it will build up the reflections off of those walls will build up on top of each other. And that's where we get the resonance from. And this is a lot like any kind of wave in a bathtub. I don't know about you all, but when I was a little kid, I would make waves in the bathtub, and you could make it so that like the water would go up on one side, but it would be down on the other, and it wouldn't really move in the middle. And so we get that when we create these standing waves in water, right? And we looked at this video in class, but I just wanted to do it one more, do it here again. So we've got the green water, right? And then we're going to stick a stick in there and start making waves. So we're going to move the water back and forth. And then you can see the antinodes and the nodes sort of form, right? So in the middle here, we've got a node. So that's where we don't have movement up and down from the water. Whereas the antinodes over here, we get a big change. We get the compression and rarefaction. And then we're going to go and do some different wavelengths of that. So we can do the next, if that's twice as short of the wavelength, right? So we get the antinode here in the middle, up and down, whereas we don't get a change right where the nodes are. And then we'll go to the next resonant frequency above that. And we get the same thing. So those aren't harmonics, right? They're just, those aren't harmonics. What they are is they're the different resonances of the vocal tract, right? So a wave, the one that was resonating at the first division, is going to have harmonics in the multiples of the fundamental above that, right? If that wave is the right wavelength for the resonant chamber, it's going to, the harmonics will also resonate in that chamber, right? However, you know, when you have different shaped chambers, you'll get different sorts of resonant frequencies depending upon what, so certain harmonics will resonate and other ones won't, right? Depending upon the chamber. And we'll talk about that more as we're going forward. Okay, so the efficiency of the resonator, remember, so this is one of the questions that I asked you all, has three things it's dependent on: the size, the shape, and the material, okay? So the size of the resonator is what matches the different wavelengths of the sound wave. The shape of the resonator will change the way that the sound waves bounce off of stuff. So we can see that in this graphic right here, where the sound waves are going against this convex reflector, and then they bounce out away from where they connect. And then if we get this concave reflector, the sound waves come in here and they bounce off, but then they meet a focal point here. And this one, the concave reflector on the right, is how things like whispering galleries, or I don't know if you all have ever been with those like cement sort of radar discs. They have one in that park that's in central, or like downtown Houston. I can't remember the name of it, but it's there. So if you're coming back next year, you can go visit it. But so you can have one person stand here, and then there's another one like across the field or something, and the sound waves will travel from one person speaking, and then they'll collect in this concave reflector, and then you can hear them in the middle. That's also how whispering galleries work, right? Then the other thing that affects the efficiency of the resonator is the material that they're made out of. So a harder surface will have sharper resonances, so it'll be more strict about what it'll resonate. Whereas something that's a lot softer or wet or has a different sort of material composition will change the way that the sound waves reflect. So I don't know if you all remember, but in our classroom at Rice, there was these sound panels all around the walls. And the reason that they're there is because it'll cancel out some of the resonant frequencies in that room. So it'll be a little less live. It'll be a little bit more dead, right? And so those materials have, let me shut off my email. Sorry, guys. Those materials will sort of suck up some of that resonance frequency and change the way that those standing waves will work. But if they weren't there, the hard surface would be a little bit of a sharper reflection of the sound. So 3 things: size, shape, and material. All right, then we talked about the constructive and deconstructive resonance already. So that brings us into phase shifting. So phase shifting occurs when sound passes into a new medium or density of air. Some of the energy is reflected away from that new medium. So we can see this every day when we look at reflections through windows, right? So a light wave will travel through the air and it'll hit the glass, and some of that light will go through the glass, right? But some of that is also reflected back towards us. The reason it's reflected is because it's changing mediums from the air that it's going through when it hits the glass. And so that light will actually shift phase and reflect backwards towards us. So if the light is at a point of compression, when it hits that, it'll shift into a point of rarefaction and reflect back. The reason that the voice does this is because of a thing called impedance. And that's when the change of pressure in the vocal tract to the air on the outside is different. So the pressure outside of the vocal tract is lower than the pressure inside of the vocal tract. And so when the sound wave is escaping, it's not met with the same sort of pressure that it's experiencing inside. And so it has a change of medium, right? The air density on the outside is less than what's on the inside. And so we get that reflection of sound back towards our glottis in the vocal tract. Okay? So that happens at the mouth, right? When the sound comes out, when it reaches the mouth, it hits that less dense air, and then some of it will reflect backwards. So, because of phase shifting, our mouths function as something called a quarter wave resonator. And that's a tube which is open at one end and closed at the other end, okay? And because of that openness on that one end, that sort of chamber will resonate wavelengths that are 4 times as long as it. So remember when we had the standing wave, we had the closed ends of the tube, excuse me, the closed ends of the tube would resonate a wave that was equal on the inside of that tube. However, with the quarter wave resonators, the sound wave needs to be 4 times as long, or a division of that, to be, or a multiple of that, to be resonated by that tube. And so it's important to remember that right now we're talking about sine waves resonating in uniform tubes, right? So the voice is more complicated because it's not quite a uniform tube and we don't use sine waves through it. And we'll talk about that when we start talking about perturbation theory in a little bit. So here's my little graphic of the 4 steps of the quarter wave resonator, okay? So when the vocal fold opens here, the red opens, the sound wave goes out. And then it bounces back, hits the closed glottis, goes out, shifts phase, and comes back. And then it makes a bit of a thicker line there. Okay? So when that sound wave is coming out here, it's shifting phase at the entrance, or at the opening of the mouth, right? So we get the phase shift here, the reflection bounces off, And it keeps the same phase here because the glottis is closed, right? Open, phase shift, reflection, phase shift again, and then bounces off at the same time that the vocal folds are opening again. So we get that combination of that reflection of the sound wave through the vocal tract combining with the change of pressure with the vocal folds opening. So the sound has to travel the length of this resonator 4 times. And that's why we call it a quarter wave length resonator, right? So that's 1, 2, 3, 4, and now it's resonant, right? Okay. That can be a little confusing, so if you have any questions, make sure you reach out and let me know. So let's move on. So that was just talking about one single sine wave, right? But so that quarter wave resonator will also resonate frequencies that are in multiples of that, right? So we're not talking about harmonics right now. We're just talking about resonances of the vocal tract. The first resonance will be 4 times its length, right? And the second resonance will be 4 times its length divided by 3, right? Because it has to go through an odd number of times. And we can do that continually, right? And so if we used a 0.68 meter resonant wavelength, which comes from a vocal tract, that like standard 0.17 meter vocal tract that we've been talking about this whole time, means that the wavelength of the sound that it will resonate is 0.68 meters, right? So if we have a vocal tract that is 0.17 meters long, it'll resonate a wavelength of 0.68 meters. And that frequency of that wave is about 504 hertz. So then we can keep doing this math up and up and up to shorter and shorter wavelengths, and the frequency will raise each time. So you'll notice that it actually skips harmonics in this, right? So if we thought of this in harmonics, the 504 hertz would then have another harmonic if you doubled that, right, at the 1008 hertz. But we skip that one, right, because that wave would be deconstructive in this sort of resonance chamber, right? So we'll have resonant wavelengths and non-resonant wavelengths, okay? So the first resonance would be a quarter, right? But if it was a half, right, so if it was twice as long, that one would cancel it out when it went through the phase shift. So we'd have that wave exiting here, and then it would reflect with the phase shift, but then it would be opposite, right? So then we would get deconstructive resonance. That's why those resonances don't resonate very well. Okay, let me double check my questions. Yeah, so the phase shifting is super, super important because of the change in phase at the end of that vocal tract. You'll get deconstructive resonances if it's not in the right sort of wavelength. I remember showing you all that with my didgeridoo, so hopefully you kind of remember how that works out. And actually don't have it here because I'm in San Antonio right now. So, okay, so then let's talk about the source filter theory. So this is kind of where the rubber hits the road with this stuff, right? This is where we really start to care about acoustics when we start talking about the voice. So source filter theory takes the harmonics that are created by the glottis and maps them onto the resonances of the vocal tract. So we've got two different things working out right now. We've got the harmonics and the resonances. Okay. So when we have those harmonics go through the vocal tract resonances will filter those harmonics and make them have a sort of different curve. So what we're looking at over here on the right is the power spectrums, right, that we talked about. So just at the source, we're going to have this shallow-ish spectral slope. So that's what's coming out of the vocal tract in terms of like harmonic energy. Then the resonances of the vocal tract will map on top of that. And then what we end up seeing is what's down here. Okay. So when we look in Voce Vista at the power spectrums, all we see is the different amplitudes of the harmonics. We don't actually see the resonances. Okay. All right, let me double check my questions. Right, good. Still moving on. So that's the source filter theory, right? That we have the source of the broadband harmonic spectrum created by the vocal folds, gets filtered through the resonances of the vocal tract, and then we end up with this sort of curve to the harmonic spectrum down here. And what that curve is like is how we get timbre, right? So if this curve is changed a little bit, we'll hear timbre in a little bit different way. These are also how we end up hearing vowels, right? So if this hump is right here as opposed to right here, if it was over here, we would hear a different vowel sound than if we heard it right here. All right. So frequency and the limit of resonance resolution. So source filter theory has sort of this issue, right? Because if we change the frequency of the fundamental oscillation, when we raise that up, the harmonics become further and further apart, right? So this is just kind of a graph. It's not like scientifically absolutely sound, although these do have logarithmic relationships. These just aren't necessarily A3, A4, and A5. So if we pretended like the top one was A3, it would have these harmonics going through this resonant vocal tract, right? So the gray dotted line is the resonant vocal tract, and the harmonics are the bluish lines on bottom. So through the source filter theory, we would end up with this sort of power spectrum. And then what we would end up inferring in our hearing is we would hear this sort of resonance curve, okay, in the green line. So we don't actually hear this gray line, even though that's the potential of the shape of the vocal tract. We end up hearing this green one over here. So if we raised that fundamental oscillation up an octave to A4, moving it over to the right here, and then spreading out these harmonics, we get a shape that looks like this after we go through that source filter, or through the filter of the source. And then we end up with this yellow line that we infer as the resonances of the vocal tract, which looks very different than this green one up here. If we raise that A4 up another octave to A5, moving it to the right again another spot, spreading those harmonics out again, we get this sort of shape after it's filtered through the vocal tract, and then we infer this red line as the resonances of the vocal tract, which is very different than this green one, or even the actual potential of the vocal tract over here. Okay. So if we stack all those on top of each other, we get some very different looking resonances, right? So we are hearing this green, the yellow, and the red, depending upon what note we're sending through that resonator, whereas the resonator potential is this blue one. So we don't hear all of those resonances, right? And that brings us to our next question, which is what was the difference between formants and resonances, right? So the formant is what we perceive to be the resonance of the vocal tract. So the resonance, let me read my slide here. When we changed the frequency of the complex wave, what we could infer from the resonance shape was dependent on where that frequency was. It significantly changed as the pitch rose, right? So the resonance is the potential of the shape, whereas the formant is the perceived resonance of the shape. And the difference between these words is really important, because when we talk about formants, we're talking about what we perceive as the resonance of the vocal tract. and the resonances of the vocal tract are the potential of that shape. So a lot of times people who have read this book, Your Voice and Inside View by Scott McCoy, um, he likes to say that a formant is a resonance of the vocal tract. And that's sort of like your mitochondria is a powerhouse of the cell sort of saying in vocal science. But what a formant is what we perceive to be the resonance of the vocal tract. And that changes depending upon what the pitch that you're singing is, right? Because you can't get that resolution of what those resonances are in the vocal tract if your pitch is too high, right? Because it's above some of those resonances and you don't actually hear them. Okay. So another analogy that people like to talk about when they're talking about this stuff is that the formants and resonances are like the wind, right? So you can see the effects of the winds, you can see the effects of resonance, or we can hear the effects of resonance, but we can't actually hear that resonance. So we can see the effects of the wind, but we can't actually see the wind. Okay, I hope that's clear. So now, this is where we're getting ahead of where we got in class last time we talked. What was it, 3 weeks ago? 2.5 weeks? It was a long time ago. And we're going to start, this is subglottal resonances and nonlinear source filter theory. So this gets a little bit heady, but I think it's important. So the vocal tract has resonances. We're talking about supraglottal resonances, so resonances that are above the glottis. However, the vocal tract below the glottis is also shaped like a quarter wave tube resonator, right? And so those changes in pressure, because the resonances are actually the changes in pressure with the sound wave, right, can add constructive or deconstructive properties to the closure of the vocal folds, okay? So the frequencies that deconstructiveness happens at has to do with where the middle passaggio is in our voices, right? So if we're talking about the top of the bass clef-ish or the bottom of the treble clef, where we all feel that passaggio, right? Depending upon if you're male sex or female sex singers, everybody has that sort of part in their voice where it feels really, really weak. And the reason is because of the subglottal resonances in the vocal tract. So the resonances of your trachea and everything down into your lungs have effects on those sorts of pitches. And so the pressure waves that are being exerted by those resonances under your vocal tracts can either help close your glottis, which is called an inertive setup in your vocal tract. And so if there's negative pressure happening in the resonances of the subglottal vocal tract, so there's less pressure when the vocal folds are trying to close, that helps them to close. If there's more pressure because of that resonance in the subglottal part of your vocal tract, that the increased pressure keeps those vocal folds open and makes it harder for them to close. And so where that happens is at about G sharp 3, right? So that's like top of the bass clef. And then at C5, which is like where the beginning of the beginning of the top of the treble clef, right? So that's where the sopranos and mezzos start to feel that change in like C to E range. That's happening around this C5 right there. So that's part of why singing through the passaggio is so difficult, because you're actually trying to counteract an inertive or constructive or deconstructive pressures that are happening below your vocal folds. And so you're having to change things a little bit to try to like counteract those measures. I think it's fascinating that there's this part of the vocal tract that's kind of like hindering where we're singing those resonances. Anyway. Okay, transient voice theory. So this is actually a very new sort of theory proposed by Julian Chen in 2017. I think he wrote a book and a really cool article. If you want to look it up, I don't remember what it's called. Sorry. But it basically is talking about how we don't know how harmonics are made in the human voice, and I've hinted at this a little bit around it during this class. But we know that harmonics come from the division of strings, right? So if you take a string length, you divide it in half, you're going to get an octave above that. If you divide it in 3, you're going to get the octave in the fifth above that. If you divide it in 4, you'll get 2 octaves above that, and so on, right? But so why do we get those in the vocal tract? Because the vocal folds are not actually strings, right? They're just little flaps of muscle opening and closing, stopping and letting the air flow through, right? That's all they are. They're just a valve going open, close, open, close, open, close, essentially with some more actions to it, right? So one of the ideas that Dr. Chen talks about is that their harmonics are made by the decay trails of the vocal tract. So when the vocal tract is set up in a certain way, there will be longer resonant. So, sorry, let me restart. So the vocal folds emit broadband acoustic energy. So that's acoustic energy that's across the whole spectrum, right? And then because of the resonances of the vocal tract, some of that acoustic energy lasts a little bit longer, right? And so that's where we end up with harmonics, because when they're created with periodicity, right? So over and over and over, we get the harmonics because of those sort of the echoes sort of the periodicity in the vocal tract. Okay. It's kind of complicated, but basically you might run into this if you get older and you start like really studying voice science and you're trying to get into teaching stuff, because this is a hot new topic, right? But the pedagogical ramifications of this are none. Okay. We can look at the harmonics created by the periodicity of the vocal folds and the resonances, and we know enough information to talk about how we're going to do vocal pedagogy. We don't have to split hairs and talk about how harmonics are created in the vocal tract. So if we just look at this like it's a source filter setup with harmonics, we can do everything we need to know about pedagogy going on. So that's what we're going to do. All right. So perturbation theory. So we've got 2 questions that we're going to talk about with perturbation theory that you're going to have to answer. And I just want to remind you what they are. So the first one is, how are resonant frequencies raised or lowered according to perturbation theory? And the second is, how does perturbation at different points in the vocal tract change vocal style or timbre? And that has to do with the video that we're going to talk about at the end. So first of all, we need to talk about what perturbation theory is. Okay, I just wanted to make sure I was still recording. So perturbation theory is talking about what happens when we change the shape of the vocal tract. So far, we've only talked about an even vocal tract, right? So a tube that's just even along both sides. However, we all know that the vocal tract is not like that. It has openings and closings, and it changes shape as it goes through. So where a tube's diameter is reduced affects different resonances differently, depending at where that reduction in diameter happens in the vocal tract. Okay? So for example, squeezing at one location, and I mean squeezing just by reducing the diameter, right? Not actually squeezing when we're singing. That's a different way. We'll use that in pedagogy. But squeezing at one location may be close to a node of one resonant wavelength, but an antinode of another. In that case, it raises the frequency of the first, but lowers the frequency of the second. Okay? So where we reduce that diameter in relation to where the nodes and the antinodes are in the vocal tract changes where the pressure is happening in the acoustic wave going through the vocal tract. And so if we change the pressure, then we change where those resonant wavelengths are, right? So remember that we resonate at the odd lengths because of the quarter wave resonator. So the 1/4 wave, 1/3 of that, 1/5, 1/7. And the two resonances of the vocal tract that we adjust when we're changing our vowels are the first resonance and the second one, which is the 1/3 of that. Because the vocal tract is not a uniform tube, where that tube is misshapen in regard to a node or antinode will determine whether or not that resonance frequency raises or lowers, right? So when we move our tongue and change where the reduction in diameter of that tube is, we're changing where the nodes and the antinodes are in that wavelength, and that's how we change where the resonant frequencies happen. Okay, this is kind of heady, so I hope you're with me. So how do we raise the frequency of a resonance? So if we're talking about just one resonance, not like the multiple ones that deal with the harmonics, we constrict at an antinode. Remember, the antinode is where the biggest point of compression or rarefaction happens in the sound wave, or we shorten the tube. Okay? So I made these little GIFs, by the way, just so you know. I can kind of toot my own horn. So we can either constrict at the antinode, and that'll reduce that resonant wavelength, or we can shorten the tube, and that also reduces the resonant wavelength. So that constriction at the antinode changes where that pressure builds up, because it builds up a little bit short of that constriction, right? You can just imagine trying to like have water go through a tube or something like that. When that constriction happens, it shortens that resonant wavelength by changing where that pressure happens. So that's how we raise frequencies of a resonance. Okay? If we want to, if we want to lower the frequencies of the resonance, we constrict at the node. So remember, that's where there's the greatest point of pressure, but not a lot of movement with the air. And so when we constrict at the node, we're pushing that pressure out to the side, and so we're lengthening the resonant length of that tube. And if we lengthen the tube, we will also lengthen the resonance of the tube. So those are the two ways that we lower the frequency of resonance with those tubes. All right. I hope all is clear. I'm trying not to get too deep into the science with like the nodes and the antinodes and pressure versus not, but I think we're going to have to. So let's look at the next slide. Okay. So where that tube's diameter is reduced affects different resonances differently. So what we were just looking at was changing one resonance, but we know that the tube has multiple resonances because of the different wavelengths it'll resonate, okay? So for example, squeezing at one location may be close to a node of one resonant wavelength, but an antinode of another. In that case, it raises the frequency of the first because we're constricting at the antinode, but it's going to lower the frequency of the second because we're constricting by the antinode. Sorry, I did those backwards. So if we constrict by the node, we're going to raise the frequency, and if we constrict by the node, we're going to lower the frequency, and if we constrict by the antinode, we're going to raise the frequency, right? So one of them gets raised and one of them gets lowered, right? Just depending on where that happens in the wavelength. So the reason that constriction raises or lowers the frequency is because it changes the location of greatest pressure in the acoustic wave. So remember when we looked at this graph before, we had this is the displacement, the movement of these particles up here, and the pressure is the change down here. So the greatest pressure happens where the movement does not happen, and the greatest movement is the lowest point of pressure, right? Because if things are moving, they're not exerting a lot of pressure. So if we constrict at a point of pressure, we will increase that pressure, and if we constrict at a point of greater airflow, we will decrease that airflow and move the point of greater airflow in turn the pressure to another location, right? So if we change where those airflow or pressure is by constricting the shape of the tube, we have to change what the resonant wavelengths of the acoustic wave are. Okay, so I love this graph because this really kind of helps show where these happen in the vocal tract, okay? So R1, that's the first resonance, happens with the antinode over here. And so these aren't nodes, they're actually antinodes. This is a bad graph. They used a different sort of annotation of this. But so the antinode happens at the front of the mouth, right? So depending on where we constrict along this tube length, we're going to change what happens to that resonance. If we look at the second resonance, there's an antinode that happens down here, and you notice that's not where it happens here. Versus we'll have the node here, which is much closer to the antinode on the top. So if you make a point of constriction at those point, at a certain point, it's going to have a different effect on these resonances because they're at different points in those resonance wavelengths. Does that make sense? Okay. Then in turn, we have other resonances. So this third resonance really has to do with the R sound, right? So we always use R, we're using constriction of our tongue about right here in our mouth. And that's happening at this sort of point. And so what we end up doing is we end up lowering that resonance, and that's where we get the R sound. So if we move our tongue back here from front to back with like E to oo, we're changing that constriction from up here to back here. So we're changing where both of those resonances happen. But whether it raises or lowers has to do with where it is in the pressure versus airflow movement of that resonant wavelength. Okay? All right. I hope I didn't lose everybody. But that's one of the big parts of knowing about how the resonance of the vocal tract change when we get to vowels, okay? So we're going to revisit this a little bit more when we start talking about vowels, and it might become a little bit more clear. All right. So our voices operate as this thing called a coupled Helmholtz resonator, okay? And so basically we can think about them as a tube with two sort of chambers in it, okay? So if we've got this chamber back here, that chamber is going to have a certain resonance to it, and this chamber is going to have a resonance to it, but it'll change depending upon where that constriction is. And then if we change that tube to have the big chamber in the back, whoops, big chamber in back, and the little chamber in front, that's going to change where that constriction happens also. So for a coupled Helmholtz resonator, this one will look like an oo, or it will sound like an oo if we send a sound wave through that. And this one will end up sounding like an e. And so if we've got our lips out over on the right here, this is our tongue, which is what does all the constriction, and our glottis in the back. We'll have the constriction will be right here versus in the front, and our oo will sound different than our e. And so we can model that with this awesome vowel applet that I found. Okay, and we're going to look at this in a second to hear how it sounds. But you can look down here, this is kind of a very crude representation of the different dimensions of the vocal tract. And so this one is an E vowel. So I actually did these backwards, oops, on the slide. This one on the left is an E vowel with the constriction being towards the front, right? And this one on the right is an oo vowel with our constriction a little bit further back. So let's look at what those look like in the applet. Just going to make sure that we're viewing it. It's not viewing. Yeah, it was. Sorry. Okay. It just didn't register. Okay. So you can play with this on your own if you want to follow the link that's in the PowerPoint. But so we can change our filter if we just want to use the simple ones for right now. This is our E with our constriction happening right here. And I can turn the sound on and you can hear what that's going to sound like. I can change the input frequency. And you can hear how that sounds like E, right? And you can see if I move here, if I put my cursor here, it'll show you like what's resonant in the little things down on the bottom. Do you see how like it looks a little cloudy on the left? Because that one's not where we're getting all of the good resonance. We're getting the resonance for that specific frequency, where I've got the yellow is on the right hand side. But if I go back here, I can find resonant wavelengths that are across the whole thing. Right. Okay. Sorry, I left that on. So that's our E, right? Let's listen one more time. Now we're going to change that to OO. So now we get our constriction a little bit further back. And you can definitely tell the difference between the OO and the E there. So now let's do it a little bit more advanced, right? So here's our better OO with a better shape. And then we'll change that to E. You can definitely tell the difference, right? So something that's really cool about this applet is that you can actually change the shapes yourselves just by clicking and drawing. So you can come up with your own sort of sounds. Or something like that. Anyway. Go ahead and take a look at it, and you can play with it on your own. I think it's kind of fascinating to see like what that does. So when you know about the perturbation theory and how that changes where the resonant frequencies are, you can kind of play with that in the applet and kind of figure out what happens. Okay. So now let's look at this Tylee Ross video. So what he's going to demonstrate is how the differences in where the constriction are on the vocal tract change how we hear differently in style. But doing that through an MRI machine. Okay, so he took an MRI of his vocal tract while he was singing, and he's singing Nessun Dorma actually in a whole bunch of different styles, and you can see how the different positions of where the constriction is change the way that the resonant frequencies work. So let's go ahead and watch it.
Singing in the MRI, singing in the MRI, singing in the MRI, singing in the MRI. Hi, my name's Tylee Ross. I'm a singer, voice teacher, and vocalist in New York City. And using the magic of MRI technology, I want to show you what it looks like inside my head and neck while I'm singing. But first, let me warm up on a lip trill. How about a raspberry? Weird, right? Want to see that on an ooh vowel?
Notice the constriction in the back of his throat.
Now, before I go any further, let's try to figure out what it is we're actually seeing here. Let's go back inside and see if we can identify some of the features of the vocal tract.
Right there, right?
Lips, tongue. This difficult to control piece of anatomy is called the velum or the soft palate, but you can think of it as the nose gate. It opens and closes, controlling the flow of air and sound up into the nasal cavity. In most people, the velum is opening and closing constantly when we speak and sing, and we're barely even aware of it. Down here, we have the larynx, which houses the vocal folds. Now let's see what happens inside the vocal tract when we sing with contrasting singing strategies. I'm going to sing the end of Nessun Dorma, Puccini's great aria. I'm going to sing it in 4 different vocal styles. The first will be in a light mix. The second, in a forward-facing Broadway sound. The third, in a back and down operatic sound. And the fourth, in a style that will make Puccini roll in his grave, in a rock style. All'alba vincerò, vincerò, vincerò. vincerò, vincerò, vincerò. All'alba vincerò, vincerò, vincerò. All'alba vincerò, vincerò, vincerò. What you're looking at here are comparative images of the same vowel being sung at the same moment in each vocal style. This is a frozen moment showing my vocal tract singing the E vowel on a high B flat. Now, for those of you who are interested, that's the E, as in vincero. Let's listen to it on a loop. Take a moment to see for yourself how the anatomical features of the vocal tract that we can see here align differently in each style. How is the tongue positioned differently? How about the velum? The mouth opening? How about the height of the larynx?
All right. Okay. I think what's really, really great about this, so if we go back to when he had all four of these up here, we can see where the constriction is different in each style, right? So remember that the constriction is what determines what that timbre sounds like, right? It also determines the like specificity of your vowel and all that. But it also determines your timbre because it's going to change where those resonant frequencies are, right? And the resonances, when they change, they'll change the timbre because that's what they are. And so we've got a different sort of shape here, especially compared to the opera one here. We're looking at this black space in the middle. That's really what we're trying to see the shape of. The forward one is a little bit different than what's up here. And that rock one has a very different shape, especially than the opera one. So, when I'm asking you the question, what does perturbation at different points in the vocal tract change vocal style or timbre? I want you to talk about that, right? That it's when the dimensions of the vocal tract change, they're changing the resonances and how the different resonances, what the positions of them are. And so we get a different timbre that way. Anyway, I think it's really fascinating. And it's actually not that crazy to think about when you kind of like break it down really easily. So, anyway, I hope you found this one interesting. Next, we're going to be talking about, oh, I forgot which one it was. I'm looking it up really quick. Next, we're going to talk about vowels and singers formant. So that's kind of like two sections together that I'm kind of going to pack together. And vowels will kind of sort of help to expand upon what these resonances do and how they change depending upon what vowels we're singing. Also, remember to sort of review about what the bark scale was and how the critical bands work because that has a lot to do with how we interpret what vowels are too. And we're going to be talking about that in the next one. All right, thanks guys.